Hello everyone, I'm Yun-Hao Zhang. I'm a final year PhD from the University of Edinburgh and Leiden University. Today I will give a talk on my recent research progress with the title of Enhancing LSST Precision Cosmology, while data augmented photometric redshifts and machine learning marginalization. Here is a brief introduction on two methods of estimating photometric redshifts. One is to use a library of SCD templates to fit the observed broadband photometry and get the minimum chi-squared results. However, it can be biased if there is a limited prior knowledge of the stellar populations. Another approach is to use galaxies with precise redshifts, usually taken from spectroscopic surveys, and then employ machine learning algorithms to find out the complex mapping between galaxy broadband SCDs and spectroscopic redshifts. But in practice, it's expensive to get high-quality spectra for faint and distant galaxies, making this data-driven framework suffering from the incompleteness in the training datasets. So in this talk, I will introduce the data augmentation technique, which uses synthetic catalog to compensate missing information in the spectroscopic samples. The first topic of the talk will focus on the dataset construction for LSST and validation on the effectiveness of data augmentation.
Here, I will describe two distinct mode galaxy catalogs we use for our analysis. One is the Cosmology 2, shown in green dots in the figure. Another is the Open Universe, shown in orange dots. These two mode galaxy catalogs share the same cosmological large-scale structure, but implement different stellar population modeling. The Open Universe catalog shows more smooth distribution in the color redshift diagrams, but the Cosmos DC2 has unphysical discrete features due to the limited number of SCD templates. So, we choose the Open Universe catalog as the realistic observed dataset for LSST. The Cosmos DC2 catalog will be used purely as a simulated dataset for data augmentation. We notice these two catalogs have overlap in the color redshift space, especially for I-Z and Z-Y color, and galaxy at lower redshifts. However, they show discrepancy for the U-G color distributions, especially at faint ends and high redshift regimes. This difference actually represents a realistic scenario for data augmentation, where simulated catalogs will not be exactly the same as the observed catalogs. This is one major limitation of the data augmentation. Here is a flowchart showing our definitions on different datasets. Application datasets are basically the photometric samples from the Open Universe catalog for LSST under 1-year and 10-year survey depths. Degradation datasets are spectroscopic samples we expect to have when we conduct LSST cosmological analysis. We provide a wide array of or possibly available spectroscopic surveys to investigate the effects of spectroscopic selection function on photometric redshifts. The augmentation datasets are simulated Cosmos DC2 galaxies, which are added to our spectroscopic samples. After merging the degradation and augmentation datasets, we will have a more representative datasets for training photometric redshifts, referred to as the combination datasets. To replicate the photometric dot selection for LSST, we initially implement realistic photometric arrows on mode galaxy from the Open Universe catalog, and then we estimate the shear measurement noise, which is assumed as a function of the galaxy I plus R band signal-to-noise ratio, and the squared ratios between galaxy and PSF sizes. Then, we select a galaxy with shear measurement noises smaller than the intrinsic shape noise. In addition, we incorporate magnitude cuts following Gauss sample defined in the LSST DESC science requirement document. We create 500 plus 1 application datasets with different realisations of photometric noise. Subsequently, we create also 500 plus 1 spectroscopically selected datasets to provide a wide range of all spectroscopic survey possibly available for LSST cosmological analysis. For each experiment, we randomly choose the upper limits in the redshift and I-band magnitudes, also a linear cut in the color magnitude space, as well as a logistic functional form of spectroscopic success rate. In this way, we ensure each spectroscopically selected dataset has one unique selection function. In the next, we randomly choose multiple realisations of the spectroscopically selected datasets and merge them into a single degradation dataset, thereby simulating scenarios where compilation of multiple spectroscopic surveys are conducted. This procedure is also repeated over 500 plus 1 experiments to ensure consistency with photometric application datasets. In this slide, I will illustrate how we perform the data augmentation. First, we train a machine learning algorithm, Self Organising Map, on the photometric application datasets to project the galaxy SED space into a 2D map. Then, we apply the pre-trained sum model to the spectroscopic degradation dataset, and we can clearly identify regions that are sparsely sampled while spectroscopic observations. Next, we take simulated galaxy from the matched Cosmology datasets to compensate the missing information. In this way, after combining the degradation datasets in the top right and the augmentation datasets in the bottom left, we obtain a more representative combination datasets. In the color diagram, the photometric application datasets and the augmented combination datasets show closely aligned distributions. As noted previously, the U-G and G-R color differ substantially between Cosmology and Open Universe. Hence, prior to data augmentation, we employed sum-based weighted sampling to resample the Cosmology galaxy, aligning their distribution with those of Open Universe in the sum space. This approach effectively mitigates catalog discrepancies and enhances the robustness of our data augmentation technique. Ultimately, our data augmentation procedure effectively extends the galaxy sample to the fan end and to higher redshifts. In the bottom left panel, the blue histogram showing the redshift distribution of the combination datasets closely match the black histogram of the application datasets. Subsequently, we train our photometric redshift estimator on the combination datasets using FlexiBoost, which decompose the conditional redshift probability density into a forward basis and uses random forest regression to infer the corresponding coefficients. We then take the redshift at the density peak as our point estimate and define the length and the source sample accordingly. In the right-hand panel, the comparison between photometric and true redshifts exhibits excellent agreements for the combination datasets, proving the robustness of the regression. However, when extrapolating the optimized photometric redshift estimator to the photometric application datasets, its accuracy gets worse for the high redshift galaxies, owing in part to the photometric noise and mismatches in galaxy SEDs between Cosmology and Open Universe. The resulting biases in the length sample satisfy our scientific requirements. For the source sample, low redshift galaxies exhibit acceptable bias level, where high redshift galaxies induce larger biases. However, compared to the left figure, the right figure, where no data augmentation is conducted, displays catastrophically biased photometric redshifts for high redshift galaxies. In addition to point estimates, we also assess the performance of the conditional density modeling. Showing here are histograms of the probability integral transform (PIT) values, which are the CDF quantile evaluated as the true redshifts. For an ideal conditional density model, these histograms should be uniform. For the lens sample and for source galaxies at a redshift smaller than 1.5, the PIT distributions remain close to uniform, indicating good performance. As noted earlier, high redshift galaxies introduce substantial deviation from a flat distribution. Nevertheless, data augmentation significantly reduces these deviations. Here we present 6 distinct statistical metrics to evaluate the performance of photometric redshifts, with data augmentation denoted in orange curves compared to without data augmentation denoted in blue curves. From top to bottom, the panel displays the mean bias in the point estimates, the standard deviation of the bias, the outlier fraction, the catastrophic failure rates, the deviation of the PIT distribution from the uniformity, and the deviation of the CDF from the true redshift distribution. In each case, data augmentation reduces both bias and information loss, thereby demonstrating its efficacy in improving photometric redshift estimate. Here we briefly summarize our first topic, the introduction of a sum-based data augmentation technique, and its proved effectiveness in improving photometric redshift performance, both in point estimates and in conditional density modeling, when applied to realistic LSST photometric and spectroscopic datasets. In the second topic, we demonstrate how this data augmentation technique may be extended to calibrate ensemble redshift distributions for LSST cosmology. Based on the existing point estimates, we partition the lens samples into 5 tomographic bins of equal redshift width, and the source samples into 5 bins containing equal numbers of galaxies. The resulting ensemble redshift distributions are shown in the figure, where the black lines represent the true redshift histograms. The blue lines correspond to the sum direct calibration, the green lines to the stacked flexi-boost PDFs, and the orange lines to the geometric average of the 2 calibration estimates. For the lens sample, all 3 methods yield consistent calibration results. However, for the source sample, the sum direct calibration exhibits extended wings, resulting in an overestimate of the distribution width. In contrast, data augmentation enriches the training datasets and significantly improves the photometric redshift PDFs. Stacking alone recovers the overall shape but smooths out sharp features, versus the geometric average of the 2 methods restores the finer structure details, similar to a self-calibration technique. To mitigate the impact of the spectroscopic selection function and the conditional redshift distributions, we have developed a probabilistic sampling technique. We model the marginal redshift distribution as a linear combination of the conditional redshift distribution, imposing direct rate priors on the coefficients. This framework propagates both the statistical uncertainty of each conditional distribution and the systematic uncertainty introduced by the spectroscopic selection function into the resulting marginal redshift distribution, as illustrated in the figure for LSST Year 1 lens and source samples. Here we show the expectation values of the marginal redshift distributions exhibits minimal biases for the lens sample, thereby satisfying LSST science requirements. For the source sample, the first 4 tomographic bins with redshift below 1 displays acceptable bias levels, while the highest redshift bin has a larger bias as expected. Moreover, the scatter in these expectation values for the source sample significantly exceeds the gray band in the figure, which represents the statistical uncertainty requirement, indicating that systematic uncertainty dominates. The correlation matrix indicates that the expectation values for the lens sample are largely independent across tomographic bins, reflecting the precision of their point estimates. In contrast, for the source sample, biases in the point estimates scatter galaxy between bins, inducing strong cross correlations, particularly between the first 2 tomographic bins. In the second topic, we show how the data augmentation enhances the calibration of ensemble redshift distributions by incorporating a probabilistic sampling framework to synthesize both statistical and systematic uncertainty components. We find the systematic uncertainties dominated over statistical ones. Finally, we briefly discuss an improved way to parameterize redshift distribution uncertainties for marginalization in cosmological analysis. Conventional parameterization assumes fixed redshift distribution shapes and permits only shifts along the redshift axis, thereby neglecting higher-order effects. Tests using principal component analysis (PCA) on the redshift distributions indicate that nearly 100 eigenvectors are necessary to recover over 99% of the total variance. Consequently, a more efficient dimensionality reduction algorithm is required. Here we leverage a variational autoencoder (VAE) to define more flexible nuisance parameterizations. Comparable to a nonlinear PCA, the VAE employs a neural network encoder to compress the redshift distributions into a low-dimensional latent space. After resampling the latent variable, the redshift distributions are reconstructed via a neural network decoder. This flowchart illustrates our combined PCA plus VAE architecture, which efficiently compress the redshift distributions into just 5 latent variables. Furthermore, our loss function compresses terms that minimize discrepancies in the mean, standard deviation, covariance, and screwness of the reconstructed redshift distributions, together with a KL divergence term to regularize the latent space to a standard normal distribution. Ultimately, we employ only 5 Gaussianized latent variables for both the lens and source samples to reconstruct the full covariance matrices of the redshift distributions. In the 2 central panels, the colors of the solid lines indicate the value of a single latent variable, and the variations in the distribution shapes are recovered in a strongly nonlinear manner, demonstrating far greater flexibility than shift-only parameterization. PCA plus VAE model can serve as an alternative nuisance parameterization for LSST cosmological analysis. We are currently performing forecasts to investigate the impact of the marginalization techniques on cosmological constraints. Below is a final overview of my talk. Thank you for your attention.